Hey there, welcome back to Short Takes 331. Today we're going to talk about the Fourier transform, and this is part 4, where we're going to talk about waves. And this video is going to follow very much a parallel line to our video, to our part 3 on diffusion. So in the case of diffusion, we had an equation that we wanted to solve that looked a lot like this one, but didn't have a second derivative here and didn't have this constant c squared here. It just had a first derivative with respect to time, but still two derivatives with respect to our spatial coordinate here on the right hand side. But the wave equation actually looks like this. So waves behave according to this equation. And so we have two derivatives, two time derivatives. We have 1 over c squared, which is the speed of the wave, and which of course, when it's light waves, is the speed of light. C would be the speed of light. And but we retain this second derivative here on the right hand side. And our question will be, given an initial condition, an initial waveform, which could be plucking a guitar string or something like that, how does this initial waveform evolve as a function of time? And we're going to be working on the whole real line, again, to parallel what we did in part 3 for diffusion, which in a way means simply that if we're looking at a string, the string is very, very long, and we're far away from the edges, and we want to understand what happens sort of in the middle section of the string before we get to see what happens at the edges. And if you want to study a case with hard boundaries like a guitar string or really any kind of string that's attached on both ends, then we can modify that and use a different approach for that case. For this one, we're going to propose a Fourier decomposition. This is once again very much like we did for the case of diffusion. And then our function, the function that we're trying to solve for, is a function of x and t, so space and time. And we're going to propose then a Fourier decomposition that is an integral over some Fourier amplitude, which is going to be time dependent. And then we have e to the ikx, our Fourier mode, that helps us solve for the spatial part much more easily. And then we integrate over dk, over all possible modes. Now, using our equation, we put that solution, that proposed solution, into both sides of our wave equation that we have up here, two time derivatives, two spatial derivatives, and we take those derivatives on both sides of the equation, and we get on the left-hand side simply the second derivative with respect to time, and 1 over c squared. On the right-hand side, we get ik squared down from the exponent, of course, as before. Now, that gives us an equation for this function f tilde for the amplitude, the time-dependent amplitudes. It's a differential equation involving time. The left-hand side then has these two time derivatives, and the right-hand side has minus k squared times the function itself. So what kind of functions do you know that when you take two derivatives, you get the function itself times a constant? It involves exponentials, of course. In this case, we're going to use complex exponentials because we believe that the process will produce some waves as opposed to some diffusion that decays in time. But even if you didn't assume that, you would find quickly that because we have a minus sign here after taking two derivatives, there has to be some imaginary component going around here to solve the problem. And indeed, the two solutions that we have to include, the two linearly independent solutions to the second order differential equation in the time variable are these two. So we have then our f tilde of kt has to be some constant, some e to the I ck times t, and another constant, e to the minus I ck times time. So the ck, of course, comes from putting the c squared on the other side of the equation. That's very easy to see. And you need to have ck and not c squared, k squared, or anything like that, because you have to take two derivatives to recover this minus k squared times c squared. And so these are the two available linearly independent solutions to our problem. Now we have to determine this ak and bk constants. We don't know a priori what they are, but as usual, we put forward our initial condition and we try to fix those constants with our initial conditions. They have to be the initial conditions because we're solving for a time-dependent part, of course. Now, if you evaluate this solution at t equals 0, then you get ak plus bk, and that has to be equal to the Fourier transform of our initial profile. But of course, we have two constants that depend on k, and so even at fixed k, we have two objects that we need to determine, and so one equation is not enough. So ak plus bk equals this Fourier transform of the initial profile. That's not enough to determine ak or bk, and so we need something more. And this makes sense. It's a second order differential equation, and so we ask for the initial condition on the velocity of this profile. So if you're just holding a string up and you're releasing it, then it starts from the velocity profile equal to 0 everywhere, but it may not necessarily be the case. Now, regardless of what you do, if you take one derivative with respect to time of this functional form, and you put then the time to 0, then you obtain this kind of equation where I actually missed the c here. There should be a c here, I ck ak minus bk. So if you take one derivative and you put the time equal to 0, then you obtain this equation again with a c here that I missed. And now that should be equal to 1 over 2 pi times the derivative, the Fourier transform of the derivative of our profile with respect to time. So this prime here means with respect to time. So we have to specify again the velocity profile at each point on our string or in our system along the whole real line in order to perform this Fourier transform and then obtain this f tilde of k0. Now we have then two equations with two unknowns, ak and bk, and that's how we proceed to solve our problem. So once then we're given these two initial conditions, our job is to perform these Fourier transforms to calculate then ak and bk. And once you have ak and bk, then you have everything. Then your job is to carry out this integral. So this integral for our function f of xt, our solution, is then the integral between minus infinity to infinity, ak e to the I ck time plus bk e to the minus I ck time, and all multiplied by e to the ikx, our Fourier mode, and integrated over k. This, of course, represents wave functions, or rather waves that move in one direction and in the opposite direction. So the relationship between x and time is of course, connected by this speed c, but also it tells you that the wave is moving either to the left or to the right. Here, this contribution of ak represents the wave moving to the left, and the one for bk, the wave moving to the right. Now, let's see an example to fix ideas and see how this actually plays out. Suppose that we're given a profile, and again, this is an example like we saw in the diffusion video, where the initial profile is just a delta of x minus a. So given delta of x minus a, you put it in here, delta of x minus a, you do the Fourier transform trivially, and you obtain, of course, right away that you obtain the form of f tilde of k0, but you don't have yet ak and bk because we need to put an initial condition for f tilde prime. And so for this example, we're going to assume that f prime is 0, and so the Fourier transform of 0 here is 0, and so that tells us that ak is equal to bk, and so then once we have that ak is equal to bk, then we're ready to calculate both of them. So then we have that 2ak is equal to the Fourier transform of our initial profile, delta of x minus a, and that's just 1 over 2 pi e to the minus ika. So that's very simple to do. It's again like in the diffusion example, but now we have this constants 2a sub k, that is what we're determining, and ak and bk are equal, and so we're ready to go with writing our full solution here as an integral. And so we go ahead and we're going to do that integral. So putting our solution in here into that integral, we get that f of xt is 1 over 4 pi. This 4 comes from this 2 over here that I put on the other side of the equation. And then we have e to the I ckt plus e to the minus I ckt that are just added just like that, because ak and bk are equal in our case by assumption that the velocity profile is 0. And so this e to the minus ika goes all the way to the end and it attaches to this e to the ikx. That's what I wrote here. That's the way I wrote it. Again, because ak and bk are equal, there's a common factor e to the minus ika, and so I just put it up here with the spatial part of the dependence. And now we can separate these two terms, e to the I ckt and e to the minus I ckt. If you want, you can join them together if that's how you like to do the integral. I prefer to do them separately, because then what we have is two terms that give us essentially the same answer, but with a crucial difference. And so what you see here is the first integral is e to the ik x minus a plus ct. So I just put this exponent together with this exponent. And then for the second integral coming from this other term, we have e to the minus I ck times time. And so I again group that together with the exponent from e to the ik x minus a minus ct. And so you see these two exponents are very, very similar, x minus a plus ct, x minus a minus ct. But in both cases, the integral is over k, over this prefactor here, k. And what that gives you, you can go back to one of the first few videos on the Fourier transform. What that gives you is that it's two deltas. So this object will give you a delta of x minus a plus ct, so delta of this factor here, x minus a plus ct, and then the second integral is going to give you a delta, a direct delta of x minus a minus ct. So this represents waves that are moving to the left and to the right, and of the initial condition, delta of x minus a. But they're divided by 2, and so this is interesting. So what's going on here is that given our initial condition, if you let go of that initial condition and you let it evolve according to the wave equation, half of that profile goes to the left and half of that profile travels to the right. You can convince yourself that this is, of course, this is just the same delta, but it's shifting to the left as you increase time, and this one is shifting to the right as you increase time. And so the deltas, these two deltas saturate at different points that move away from the point A as you let time move forward, as you let time grow from 0. But what's interesting that you can see here is that half of the weight of the initial profile goes to the left and half of it goes to the right. So that's really interesting. So let's try a more general example. And so suppose that we have an initial condition that is given by a general profile, which could be very much what we talked about, or where I depicted here at the very beginning. Suppose it's some weird shape like this, and not of any particular form. Let's assume that it goes to 0 at infinity, just to fix ideas and to avoid any potential trouble. And let's assume also that this is dropped from rest. So this is dropped with the initial velocity profile that is 0 everywhere for the whole wave. Now here, we can make use of our previous solution. And the way to do that, the way to take advantage of what we already know, the solution for the delta of x minus a, is to write this g of x itself as an integral. So this g of x can be written as an integral from minus infinity to infinity of g of y. Now this y is an auxiliary variable, delta of x minus y dy. So this integral, if you do it, is just g of x. There's nothing else, of course. But now the whole x dependence is into this delta of x minus y. And so this y then is going to play the role of a in our previous solution. And in a way, what we're doing is simply superimposing a bunch of solutions. This is what we're going to do, where at each point there's a g of y taking the weight of whatever happens at position y. Whereas here we just had delta of x minus a with a 1 in front. So that's really what's going to happen here. We're going to be superimposing those solutions. And you can check, you can see easily that if you do the Fourier transform of this f of x comma 0, of this g of x, then that's what you get. That's what determines a of a sub k. Our initial velocity profile is just 0, and so that means that ak is equal to bk, and so that's necessarily the case. And you can see that that's going to be true just from this equation. And here again, even though I missed the c here, the fact that the initial velocity profile is 0, then it means that ak is equal to bk for all k. And so we go back down here, we don't worry about bk then. Bk and ak are equal, and so then this is the equation that determines what ak is. So it's going to be, ak is going to be 1 over 4 pi times the Fourier transform of g of y e to the minus ik y dy. So this is the Fourier transform of g of y. And so then we go ahead and we insert our expression for ak and bk into our solution, which we wrote up here in full form. So this is going to be our ak, this is going to go in there. bk is the same, so it's the transform that I just described of g is going to go in here as well. And so we go ahead and we do that. And what you do next is that you exchange the order of integration. So we're going to have an integral over y and an integral over k. Let me go back. So here you have an integral over y, and up here you have an integral over k at the very end. So we're going to exchange those limits, those orders of integration, the order of those integrals. We're going to exchange it, and we're going to do first the integral over k and then the integral over y at the end. And so what you get, if you do that, is simply that the result for f of xt is 1/2 the integral from minus infinity to infinity g of y times basically the solution that we had before. In fact, the 1/2 is part of the solution as well. So this solution that we had before, just for the delta, plays a crucial role here, that it helps us propagate our solution, our initial from our initial condition, g of y, and it splits our solution into a part that goes to the left and a part that goes to the right, and each gets 1/2 of the weight. Because of this 1/2 here, we've done nothing else other than making use of our previous solution and exchanging the order of integration to take advantage of the fact that now we know how to do these integrals, and this is the result. So I skipped a step there. In other words, I'll leave that for you to do. It's very simple, and the great conclusion here, which is kind of cool, is that just like before, the delta splits into two deltas, one propagating to the left and one to the right, each with 1/2 of the weight. Then the same happens here. The initial profile g of x that was sitting there when you release your string, then half of that weight goes to the left and half of that weight goes to the right, and that represents the time evolution of your string the moment you let go, starting from 0 velocity. If you don't start from 0 velocity profile, then of course the solution will be a little different. Maybe a little bit more will go to the left, a little bit more will go to the right, depending on how you distribute that velocity. But that's something I will let you explore and for you to have as an exercise. And that's it. That's all I have for you today. I hope you enjoyed this video. If you did, please like and subscribe. And as always, if you're looking for a tutor in physics or math, in English or in Spanish, you can contact me at shorttakes331@gmail.com, or you can leave a message in the comment section below and I'll get back to you. And that's it. I'll see you next time.